This is a very useful formula in calculus. The left-hand side, that's exactly the sum of the first n cubes that goes from 1 cubed to 2 cubed to 3 cubed all the way to n cubed. The right-hand side in the base, n times n plus 1 over 2. From what we talked about before, that is the nth triangular formula. So this will generate the triangular numbers and then squared. So now we're going to put observation in this chart. So we second row we're going to do here is we're going to list the first few triangular numbers. Say when n equals 1, the first triangular number, we can plug into the formula 1 times 1 times 2 divided by 2. So that gives us 1. And then we're going to replace the n with the 2. So 2 times 3 divided by 2. And that gives us 3. And then plug 3 in here. We know that we can get a 6. And if you replace the n with 4 times 5 divided by 2, that gives us a 10. So we can apply this formula continually that we're going to get all the triangular numbers. And in general, the nth triangular number is n times n plus 1 divided by 2. And next, we're going to square each of the numbers because the right-hand side squares each triangular number. So we know 1 squared is 1, 3 squared is 9, 6 squared is 36, 10 squared 100. Continue this, and we get the nth triangular number squared. All right, so that's the right-hand side. Now, let's take a look at the left-hand side. When n equals 1, we're only going to get the first cube square. First cube, because the left-hand side has a pattern. It's adding the first n cubes. But if n equals 1, that means that we only have 1 cube, which is the first cube. Now, when n equals 2, we're adding the first 2 cubes. When n equals 3, we're adding the first 3 cubes. When n equals 4, we're adding the first 4 cubes. Now, we're going to check each pair. As we can see, 1 cubed is equal to 1. And 1 cubed plus 2 cubed is 8 plus 1. That is equal to 9. And 3 cubed is 27. 27 plus 9, that is equal to 36. And 4 cubed is 64. 64 add the previous cubes, 36. That is going to give us 100. So that tells us if we keep doing this pattern, adding the first n cubes, we only did the first 4 of them. We do see they always match. That gives us a conjecture. So maybe these two are equal. The first n cubes equals the triangular number, nth triangular number squared. So next we're going to prove this. First we are going to look at algebraic identity, which is sort of complicated here. The right hand side is easy. That's just k cubed. On the left hand side, we're adding a bunch of expressions. In each pair of brackets, we see that we always have a algebraic expression, k times k minus 1, k times k minus 1. And besides that, we also have 1, 3, 5, and following the pattern, we know that we're adding odd integers. The last one is 2k minus 1. And notice that we have a formula for discussed before. If we add the first m odd integers, 1 plus 3 plus 5 plus dot dot, the last one is the 2m minus 1, we're going to get m squared. Here m means the mth odd integer. So here altogether we have m odd integers. So here is later we're going to use this formula. But why does the sum of odd integers have anything to do with the sum of first n cubes? They don't look anything related. But next we're going to put another observation in the next chart. So go back to the long identity here we have. Now the right hand side is easy. So it pretty much means each integer cubed. So we're going to replace k with 1. That gives us 1 cubed. And then we'll replace n with a q. That gives us 2 cubed. Replace n with 3. We have 3 cubed. Replace n replace k with 4. We're going to get 4 cubed. And continue in this pattern. We're going to get the last one, that is n cubed, replacing k with n. Now let's look at the long expression on the left hand side. What would this generate? So notice that for the first one, k is 1. If we replace k with 1, here each of the expression I underlined will become a 0 because 1 minus 1 is 0. So 0 times another 1 is still 0. So this underlined will pretty much disappear. And what we left would be those odd integers. But notice that the odd integers we have is 1 plus 3 plus 5 plus dot dot. The last odd integer is 2k plus 1. So if k is equal to 1, that will only generate one odd integer. Because the second term is pretty much in each pair of brackets is the first k odd integers. So if k equals 1, that means we're just going to get the first odd integer. That is 1. And now let's replace k with 2. If k equals 2, we're going to get 2 times 1, that is 2. So each expression underlined will become a 2. But notice that if k equals 2, we're only going to have the first 2 odd integers. Because k equals 2. 2 times 2 is 4. 4 minus 1 is 5. So 4 minus 1 is 3. So that will only give us 1 and 3. So that's, we're going to have this and 3. Because k equals 2, we only get the first 2 odd integers. And adding that expression, the 2 generated by the expression, 2 plus 1 is 3, plus add a 2 to that 3. That gives us 5. So if k equals 2, the left-hand side will be 2 plus 1, 3, 2 plus 3, 5. So that gives us a 3 plus 5. Now next, we're going to replace k with 3. First, look at each expression. When k equals 3, we have 3 times 2. That gives us a 6. And how many terms will we have? Depends on what k is. So k, because k is 3, that means we're only going to have first 3 odd integers. So we have 6 plus 1, 6 plus 3, and 6 plus 5. And we're going to add these together. That gives us, these two give us a 7. And these two gives us a 9. And these two gives us 11. Okay, now next we're going to replace k with 4. And still first we're going to look at the expression. When k equals 4, we plug it in. So it's 4 times 4 minus 1. That is 4 times 3. That gives us 12. So we are going to add 12 to the first 4 odd integers. And there's one more which is omitted here. So we're going to write it down here. So now we're going to get 13. 12 plus 1, 13. 12 plus 3, 15. And 12 plus 5, 17. And plus 12 plus 9, 19. Now following the pattern, in general, last term will be replacing k with n. So we're going to get, on the left-hand side, pretty much we copy everything except we have to replace k with the n now. Because k is equal to n. So that would be the first plus the second. Because I don't really have a lot of space here. I'm just gonna write down the first two and the last one. The last one, sorry, gotta replace k with n. The last one we replace k with n plus 2n minus 1. Okay. All right. So next we're gonna do a comparison here. Look at the left hand side and right hand side, each pair of number. As you can see, they all match because 1 is equal to 1 cubed. 3 plus 5 equals 2 cubed. 7 plus 9 plus 11 equals 3 cubed. And we can also verify 13 plus 15 plus 17 plus 90 equals 4 cubed. So that gives us a conjecture these two should be equal to each other. So here we're not going to prove this part and just use the observation that these two are equal. So next thing we're going to do is we are going to add all the cubes because that's what we need on the left hand side of the formula. So when we add 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus dot 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 plus the very last one, n cubed, will be equal to adding all these odd integers because we just verified each column numbers they match. So now we successfully converted the problem of the sum of the cubes to the sum of odd integers. So originally we're supposed to add the sum of first n cubes, but because the cubes equals the sum of some odd integers, and as we can see, they are 1 plus 3 plus 5 plus 7 plus 9, 11, 13, 14, 15, and so on. So this is like adding a bunch of odd integers. And notice that the formula I mentioned that we already have a formula for adding all the odd integers. You take how many integers we have and square it. So the important thing is to figure out, look at what the last odd integer is. So we're gonna look at this last expression right here and simplify this. So we're gonna use algebra. Let me copy this again. So n times n minus 1 plus 2n minus 1. When we use algebra, we square, distribute n plus 2n minus 1, and combine like terms. We get n squared plus n minus 1. And we're going to do a little bit of do a factoring for the first two terms. We found that we can factor n minus 1. And then the reason I'm doing, am I doing factoring? Because I want to match the last formula we have, 2n minus 1. So the form of 2 times n minus 1 gives us which odd integer we have. So this is what I'm going to do next. I'm going to multiply this by 2, and then I'm going to divide it by 2. This way, when we cancel the 2, it doesn't change the expression. But this is exactly the format we need. 2 times something minus 1. See, 2 times something minus 1. So now we have 2 times this whole thing minus 1. Okay. So this expression circled in blue tells us how many odd integers we have. So now we have this many odd integers. That's like our m in the expression. So when we add this many odd integers, we should get that m squared. In our case, m is n times n plus 1 over 2 squared. So when we add all of these odd integers, we should exactly get m squared, which is n times n plus 1 over 2 squared. And notice this is exactly the triangular number squared. So that goes back to the very beginning, that identity we want to prove. So the last step we did is to look at the because we know the left hand side is equal to the sum of a bunch of odd integers. So we looked at the last odd integer. We found out the last odd integer is this, and which can be written as triangular number squared.